The subject of this panel is, what is quantum information really good for? And in addition to the two non-Skype speakers that we've already heard from, we have three more panelists, and I'll introduce them. Caslav Brukner is here, and Raymond Laflamme, and Sorin Paraoanu. We'll start with Soren. Each of the three new panelists will speak for 3 minutes or so on the question, what is quantum information really good for? The speakers who've already spoken may add comments as they see fit. And then, after they've all spoken, we'll take questions from the audience for any of the panelists. Okay, and we'll begin with Soren.
Hi, good evening. Can you hear me? Yeah. So I would like to start addressing this question, or to propose a topic for discussion, by using the following metaphor. Suppose you go to a restaurant. You normally are given a list by the waiter. There is a list with all the food that the kitchen can make for you. And you expect that whatever you will get will be whatever you order from that list. There's a waiter that nicely helps you to make your choice, and so on, goes to the kitchen, makes the order, then brings it back to you. Now that's the classical world. That's the classical restaurant. In the quantum world, it's not like this. In the quantum world, it's a special kind of restaurant. You just go there, and whatever the cook is cooking there, it's just throwing it at you randomly. You don't know what you're ordering. You don't know what you're going to get. You cannot rely on any waiter because there is no waiter. So properties that are listed on this menu list don't exist in quantum physics.
It's like a really excellent sushi bar.
I would say that if you could start a business with it, that could be an interesting idea. So the quantum restaurant business would make some money. But that brings me to the issue that this restaurant is economically very efficient. So you see there is no waiter. You save money on paying one person. The waiter could be, you can imagine, the space-time or causality. We don't quite have that in quantum physics, or at least not in everything in quantum physics. So this machinery, this restaurant is enormously efficient at processing, not information in this case, but processing people who are hungry. So can we use this efficiency to our purposes? That's the main issue here, I guess. What is it good for? Can we invent a restaurant, a quantum restaurant, with many of these cooks in the kitchen that would serve actually what you want or close to what you want? So this is quantum information processing, in fact. So what we now, I would like to say what we are interested in and what we think it's quite a valid line of research to pursue. And the picture in the back here is actually one of our samples that has been nicely shown to process information in some sense. So we think that we can combine ideas from, that we can put these questions about asking what is the nature of space-time and what is quantum information in the same kind of experimental setup. So we can combine a control experimental setup, we can address questions about quantum fields in curved space-times. To me, the interesting question is the things that we learn from quantum information from using like standard qubits and quantum field theory and so on, do they apply, and in what form, to space-time? Can we apply quantum information concepts to space-times? And the hope is that this kind of analog systems, like we call them, could address this question in some experimentally controllable way. That's it.
Okay, thanks. We're going to hear from all the speakers first, and then but save your questions that you're thinking of. So next we'll hear from Chasla.
So, what is quantum information good for, except for having conferences at good places, nice places? So quantum information provides a new way of thinking about quantum physics, in particular about quantum foundations. So let me give an example for that. And I think this observation I first heard from Anton Zeilinger, actually. In 50s, 60s, and 70s, the majority of the PhD students were given problems of calculating eigenstates or eigenvalues of some given Hamiltonians. But with the birth of quantum information, this has changed. And the problems were given where an agent has a participatory role in observations. So when I think about that, I think about problems such as, you know, Alice is measuring a system and provides then and sends information to Bob about her choice of setting or outcome, and Bob performs certain measurements on the basis conditional on this information. So you can think about quantum cryptography or quantum teleportation, similar things. So I think that kind of, I would say, algorithmic type of thinking was a major input for the current development in quantum foundations. And it actually sharpened our way of thinking about quantum mechanics and distinguishing quantum mechanics from classical physics. After all, even John Bell, now we have 50 years of discovery of John Bell's inequalities, who was definitely ahead of time, was in effect thinking algorithmically, because the idea was not to think about what will happen in a closed quantum mechanical system, not about calculating Hamiltonian properties, but it was about comparing measurement results of distant observers who has independent choices of measurement settings. So it's interesting to see that even the fathers of quantum mechanics use the notions of information and knowledge, and I pick up here one of them from Wolfgang Pauli on distinction between indefiniteness and unknowns. But there are many more by Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. And it's interesting to see that this was 30, 40 years before the theory of information had been established by Claude Shannon. And it took another 30, 40 years until we realized that these two notions, the notion of quantum and the notion of information, are interrelated to each other in a quantum information science. So I'm convinced that this input from quantum information was also crucial for the recent developments in quantum foundation, and the other way around as well. And let me give another example for that. We still do not have a unique, broadly accepted interpretation of quantum mechanics. One possible lessons we could learn from this unsatisfactory situation, that it might be something inherently deficient in the idea of extracting meaning of the theory solely on the basis of quantum formalism, which interpretations of quantum mechanics are. Instead of that, as a reaction to that, people have tried in recent years to extract the meaning of the theory together with the quantum formalism from a certain set of more or less plausible assumptions, axioms. That's what is called reconstructions of quantum theory, and people who work on that are also among us. And most of these reconstructions are information theoretical in nature or operational. They talk about primitive laboratory operations, what an observer can do or can't do in a laboratory. So what I want to say that this way of algorithmic thinking actually brought these new results. And the fact that we can even derive some partial or fully formalism of quantum theory in that way seems that it's very helpful and that there is some deep truth behind. Of course, bringing the information into physics and into quantum physics brought some new insight, but raised at the same time new questions. Questions like information about what, whose information? And I don't want to address this question now. I'm running out of time, and that's what I wanted to say.
Okay, thank you. And Raymond.
Thank you, Bill. I think you added one word in the question. And I had read the question as, what does quantum information good for? But you added the really good for. Which changed the tone of the question.
I mean, if it's good for something, it's good for something really, right?
Yeah, in reality, we know if you start to talk about reality, it's a slippery slope. And having left Waterloo at 2 a.m. today in a snowstorm, traveling through the US and arriving here at 5 p.m., and thank you for Andrew for taking my place at 5 o'clock to give a talk, and I'll be there tomorrow morning. Then I realized that there are indeed many worlds around, definitely a snowy one and a much warmer one around here. So what is quantum information really good for? It helps us to navigate these different quantum worlds that we see around. And to kind of paraphrase, I think I heard this from Seth Lloyd the first time, quantum information science is the right framework, the right language on which we can control and kind of manipulate and navigate the world of atoms and molecules. And I'm surprised, being the third one, that nobody has explicitly said it'll be good for quantum computing, or it'll be good for quantum communication or cryptography. So it seems to be obvious to people in the audience.
We knew you were on the panel.
You what?
We knew you were on the panel.
But so I was going to say, I'm not going to talk about these two, but maybe I should, because I think on the quantum computing part, I think it brings the computer scientists, or it makes the computer scientists think a little bit more like physicists, and the physicists think a little bit more like computer scientists. And I think this is a good marriage. I think it's places where it has been fruitful, and it will still be in the future. But I won't talk more about computing and communication, but I'm going to talk about another places where we do see impact of quantum information today, where it's really good for today. Andrew mentioned at the end of his talk, somewhere he said something like, yeah, maybe quantum things will be good to make money. Well, I think there will be a lot of money to be done with quantum information, and maybe not in that long future. In fact, there are some spin-offs that have come out in the last 5 or 6 years where I've seen, surprisingly, some small piece. It's not a quantum computer which changes the way that we really understand information, but some derivative that comes out and is being applied. And I'm going to talk about one which hasn't get yet that much money, but can be useful. So I don't have slides. In fact, I do have slides, but I was not organized enough to have only one of them to show. So I have a prop instead. So do people know what this thing is? Okay, Seth, you're too near the person.
Anyone want to jump in?
Yeah, it looks like, the first thing, it looks like something to hold letters. Or a paper, yeah, some information in there, or some weight in there.
I thought it was actually the cooling fins for a power amplifier.
Oh yeah, it's a cooling fin for my quantum computer or something like that. It's a neutron interferometer. And it's
a neutron interferometer.
Yeah. And usually you would see these little fins are called blades, and they are essentially beam splitters. And neutron interferometer is not new. 50 years ago, people have been thinking about doing neutron interferometry. People are using it to image. And usually you would see them with only 3 blades instead of 5. And so a neutron comes in one, they split in 2, they go to these ones, they converge again, and if you put a little thing here, you can image it by kind of moving it around, and you can use it. And the great thing with neutron is you can image on the size of angstroms without destroying the things you want to image. But imagine having this. You want to image on the size of angstrom, and this thing is quite big. And if it starts to move by more than 1 angstrom, then you won't be able to image things. So people do in neutron interferometry, they put this on some kind of optical table. The optical table is on some piece of concrete which weighs about 30 tons. And then you have a room to isolate for temperature gradient. You have another room for sound insulations. And then you have your tiny little sample in there. You can image things. And it turns out by ideas of quantum information, in particular quantum error correction, people look at this and they say, oh, if a neutron comes in, then you can have a state that goes at the top, which is like the 1. Go to the bottom is like the 0. And the error model is a phase. Like the 1 gets a phase which is the opposite of the 0 if the dominant mode of vibration is like this. And so you say, okay, we have quantum error correction, which I was supposed to talk about at 5, but I will talk about a little bit tomorrow at 9. you have quantum error correction. Can you make an error correcting code which corrects for that noise? And the answer is yes. And it takes 5 blades. And I'll leave this for a beach walk for anybody who's interested exactly how the deal work. But here's a simple example where ideas of quantum information have implications which are happening today. Not a quantum computer, but something which is concrete. A place where there has been money to be done is another application where suddenly you can apply ideas of quantum information to oil exploration. So if somebody would have told me this 10 years ago, I would have said, this is totally crazy, it doesn't make any sense. And it turns out that you can use, again, ideas who have been developed for quantum information to help doing imaging at the bottom of oil wells much better. And again, if anybody's interested, I can explain exactly how it works. But what is it really good for? It depends on what the really mean. If you want something which is practical, I think this is happening today, and there'll be more and more. If you want to be kind of in the real world, if you want to think about what quantum information brings you to understand the world, then I'll leave it to the first 2 speakers who are kind of focusing more on that point. Thank you.
Okay, very good, thank you. And I'd like to invite Andrew and Gerardo to add anything if you'd like to on the subject of what is quantum information good for.
When Michael Faraday discovered electromagnetic induction, somebody asked him, what use is that? And his reply was, what use is a baby? Not long afterwards, the Prime Minister asked him a related question, which was, will this electromagnetic induction be useful? To which he replied, it's too early to say, sir, but I have no doubt that if it is, you will find a way to tax it. And I don't know what it's like in the countries represented here. In the UK, it actually took about 150 years, and then they found a way to tax electricity. In the UK, some of you may know that in the so-called autumn statement, which actually happens in December, the government announced that they would put £270 million into the development of quantum technologies in the UK. And you can be quite sure that the government, well, the government's only got one motive for doing anything, and that is to get re-elected. And they think that this will help them to get re-elected because it'll be profitable for Britain, not because they think it'll answer any questions in quantum foundations at all. So I'd really echo what Ray has said, that when we're considering what it's useful for, by all means let us enjoy the intellectual pursuits for which it's useful, and let's exploit those and rejoice in them. But the vast majority of work that is done in quantum experiments, quantum technologies throughout the world, quantum information processing, is technology driven. That's why most of it is happening. Now, when I started running the national research activity in the UK for quantum information processing, which was about 10 years ago, it seemed to me then, I asked, what's the threat to the subject? Why might this die out and never be any good? And the theory at that time seemed so strong and so robust that there was no doubt about the theory, except that you can't go on forever doing theory in the absence of experiments. And it wasn't clear to me at the time whether the experiments would be comparably successful. I think it's been the case worldwide in the last 10 years that there's been spectacular progress on the experiments towards quantum technologies. And now seems to me that there's little doubt that quantum computers will be built. And as Ray was saying, there are already some other technologies en route that exploit quantum information. So what's now the threat to the subject? And I think most people would have hoped that since the development of the first sort of breathtaking quantum algorithms, the the factorizing algorithms and the search algorithms, given the spectacular potential that quantum information has for new kinds of logic, it was hoped that there would be a real growth in the number of different algorithms. Now, there has been progress. I don't want to belittle that, and each bit of progress is a significant achievement. But I still think that I hope that when we meet again and next ask the question, what is it good for, we'll be able to list many more algorithms than we currently can.
Okay. Gerardo, did you want to say?
So I agree with most that has been said, and in particular, I also believe that, okay, we can make some predictions, and we are all pushing some definite lines, but it could be that, I don't know, 30 years from now, there is some completely different and unpredicted breakthrough which will make use of quantum technologies in a highly profitable way that we cannot predict. Like for transistors, where they invented them and they said, this could be useful for hearing aids, and then they were useful for much a broader range of electronics, and I think this could be the same thing in the quantum technology situation. But I want to detach a little bit from this and just add one more topic which is different, and I think quantum information is really useful for a better teaching of quantum mechanics. So I think this allows to engage students and even the public in a much more entertaining and more useful way. So I think if lots of quantum mechanics courses needs to be revised a little bit, instead of going the traditional historical perspective, the failure of classical physics, and then going the whole year about the potential wells and so on. If they start with the qubit and with very simple application, like even teleportation, I think it's going to be much more entertaining for people to go into quantum mechanics and modern development.
I could just tell you that Bob Kirker at Oxford has a new textbook coming out next year, teaching quantum mechanics from exactly that approach.
Thank you. Well, thanks very much. So the panelists have interpreted the question in a couple of different ways, right? What is quantum information good for, and what is thinking about quantum information in its own right good for? Yes. So now questions from the audience.
So this is, I guess, maybe more of a comment than a question, but going back to Soren's restaurant example, I think this gets at the heart of something that we actually haven't talked about that I was a little surprised we haven't. So you said that quantum mechanics, the quantum world just sort of tosses out whatever at you. Well, that's not entirely true. In a sense, we can choose the cuisine, for example, of restaurant that we wish to go to, and we can even see the menu. It's just we're not guaranteed to get exactly what we order, right? So
that applies to a lot of restaurants.
Well, right, that's very true. But the point is it's not entirely random. We have some control. Basically, we have control over the questions that we can ask the universe, right? And it's this idea that nobody mentioned yet, the idea of contextuality in quantum mechanics, that the outcome of the experiment is contextual. It depends on the question that we ask. And so that's not complete randomness. It's not like, if I go to measure the spin of an electron, I'm not going to suddenly get the answer purple, right? You know, I'm going to get the answer spin up, spin down, something like that. So.
But you might get the answer spin 100.
Yeah. Sure. I mean,
but it'll still be spin. It won't be purple.
Yeah. Sure. I completely agree. Actually, you do have some freedom of yourself what questions to ask. So it's like you do have the freedom to put the detector in this direction or in this direction, meaning that you do have the freedom to walk on that street or on that street and encounter that restaurant or that restaurant. Yeah, but that's true.
Yes.
Just a postscript to that last point, John Wheeler had a famous parable of 20 questions based on exactly this notion in which there was no fixed answer in advance, and the questioner would just ask a succession of questions to which random answers would be given so long as they were consistent with what came before, and then eventually there would be a solution. And so the solution came partly from the questions that were asked and partly from the indeterminacy of nature. I thought it was a wonderful parable.
Right, and John Wheeler imagined that as a way of constructing reality. Okay, other questions? Comments? There's one.
So I wanted to comment on the point Andrew Briggs made about that, why haven't there been more quantum algorithms discovered, or it's been sort of disappointing that haven't been more. So I mean, this is a point that I hear a lot, but it's always confused me because, there seems to me to be sort of something that more or less explains the situation, which is that we simply, don't know that many examples of problems for which there plausibly could be quantum algorithms. So, I mean, there are the NP complete problems, right? Those we have good reasons to think are just, there's not going to be a fast quantum algorithm to solve them in general. Right, then there were the problems that a classical computer can already solve efficiently. So at most, the quantum computer will give you some speed up by a polynomial factor, and in many cases we do have such speed ups. So then, if you're looking for more, like let's say exponentially faster quantum algorithms, then you're stuck looking at problems that are neither classically efficient nor NP hard, and there's really only a few examples of such problems that sort of are well known, and have practical importance. For many of those, we do have quantum algorithms. Others people are like factoring, others people are working on, I mean, even if they succeed, they are sort of more abstruse than factoring. So it seems to me that a prerequisite for discovering more quantum algorithms is to discover more problems.
Well, you and I have talked about this, Scott, but I think one fruitful direction that one might go, Scott in his work has emphasized that it would be very interesting to look at other types of algorithms. In particular, if you look at algorithms that are in the polynomial hierarchy, which are problems that have access to an oracle. So you get some oracle that will give you some information. Then there we actually have good results both in classical cognitive complexity, and there may be other results for quantum algorithms. And I'd just like to give a little advertisement of it. I mean, I always really hated oracular problems. What's this oracle? The oracle is like, like this woman sitting above a vent of hot gases going, something that's her question. She says a great kingdom will fall, right? But in fact, we're living right now in an age where a huge number of very practical problems are effectively these oracular problems, because the machine learning tasks that were mentioned earlier are problems where you have a gigantic database full of big data, and every call to the database is effectively a call to an oracle. So I think actually that there may very, very well be the possibility of having some nice, good algorithms for these kinds of very practical kinds of problems, so analyzing large amounts of data in a quantum mechanical fashion.
Yeah, I just wanted to point out, I mean, this isn't a new algorithm, but I think, I sort of agree with Scott that, I mean, I almost think, maybe we understand a lot about what you can do with quantum computing and what you can't. But one of the things we understand you can do is Grover's algorithm, and I think that's going to be a huge application. If you can get a qubit for 10,000 times the cost of a classical, let's say a Q flop for 10,000 times the cost of a classical flop, a clean one, it will be all over the place in combinatorial optimization, all kinds of problems that you can formulate as a Grover search or a tree of nested Grover searches. And that's probably reflected in the amount of money that Google and Jeff Bezos are willing to throw at it. So that's one thing. The other thing is problems where you maybe don't have to find the ground state of a physical system, but you're interested in maybe transport properties where it's really important to be able to efficiently implement a unitary operation. And then maybe you can't find the ground state because that's would enable you to, at least you can't find the ground state with an exponential speed up because that would just be as hard as enable you to solve NP hard problems. But you might be able to, find out some properties of the dynamics, like what is the correlation function between this input and this output. And for some purposes, maybe that's good enough. I
was going to ask a question back to Scott. In the world of classical computer science, in the last 10 years, how many earth-shattering that would be comparable to the impact of Shor in quantum computing? How's that?
Depends what you mean by earth-shattering.
I thought you were going to say this.
Maybe there are, you know, a couple of earth-fracturing algorithms every year or so. But I think that that's an excellent point. I completely agree, right? That, you know, also in classical computer science, what you usually find are, you know, a few ideas like, you know, Markov chain, Monte Carlo, you know, dynamic programming, right? That just get applied over and over, you know, in different contexts, right? So when people say, well, all the quantum algorithms are really just, you know, the Fourier transform or amplitude amplification, you know, just used over and over in different contexts, right? So, you know, it's the same, it's exactly the same situation with classical algorithms. You know, so I mean, there have been, you know, the biggest breakthroughs, I think, in classical algorithms, you know, in the last 10 years. Well, I mean, there have been things like for dealing with sparse data sets that have been pretty important. The biggest theoretical breakthroughs have been like in giving deterministic algorithms for things where we previously only knew probabilistic ones. Right, and that's theoretically very important, but practically it's not important because the probabilistic algorithms were just fine in practice.
Okay, Max?
Since we've encouraged a lot of people to speculate about the theoretical future here, I was wondering if we could also get the experimentalists to speculate a bit more. If we take this a concrete question, like how many years do you think we have to wait until a quantum computer will out-factor the world's fastest classical computer? I'm just curious if each of you guys up front could just throw out a number.
So can I add to that? So I live in Seattle, which is south of Vancouver, right? And you hear about D-wave all the time. Can anybody from you tell me this D-wave, is that truly quantum computation? So I take this now. I'm not taking this one.
I was going to send it to you, Scott.
Yeah, you can take this one. You guys are all experts. You can't get out of this. Is it a quantum computer or not?
So if I can comment on those two things. The first one, as far as what D-wave actually does, nobody knows, but we're at Oxford, we're about to advertise for a postdoc to work for 3 years, industrially funded, to address exactly and precisely that question. So if any of you has a student or would be interested or has a friend who'd like to apply for that position, come and join us, and then in 3 years' time I'll tell you what we found out.
Nobody today has replicated their results.
The other,
but replicated, you mean build a similar device and see how it works? The answer is no.
The other question you asked is, you know, when will a quantum computer outperform a classical computer?
Yes.
And spurred on by this sniff of the 270 million from the UK government, we've actually done rather a detailed analysis in Oxford. And we think the answer is 2020.
2020.
So
that's
in 6 years.
Pardon?
In 6 years' time.
Yes.
That's the hard part.
Okay.
By normal arithmetic.
And this is recorded, you know.
I would love to hear what you sitting there, what you think. So
I have a bet.
Shorter?
I have a bet with Ben Schumacher that by 2020 we will not have a quantum computer which beats a classical computer. And the bet was done in 1999. So
I hereby publicly announce, you are all witnesses, that if you are right, as compensation, I will give you dinner on high table at my college in Oxford. And if we are right, I'll invite you to dinner on high table to celebrate.
So I like this. I'm on a superposition of winning.
So put it in your diary.
Anyone else?
Yeah, so I wouldn't say anything about quantum computing as such, but I think quantum simulators are coming quite fast in the next decade or so. I'm in fact, quite hopeful that they will come. So this is something to look forward next. And to come back to the other part of the question, I think, and that's related also to the question that Carlo Roveri addressed, Andrew, what drives the experimentalists, and why should we continue doing experiments in foundations? So, well, one of the things is that since the question was addressed by a theorist, and there are so many theorists in the audience, that you have to know that we, the experimentalists, we do trust what you guys are saying to us. So it's a great responsibility on you also that whatever you tell us, we will try to, you know, go there in the lab, put some circuits and see if it works or not. The other thing is that, in my opinion, there are a lot of things that came up and we don't quite see them so clearly because they are not really the quantum thing that people thought that they will be, but they are there embedded in the technology. This happens also generally with nanotechnology. You don't quite see the nanotechnology gizmo, but it's there in your clothes, in your materials, and so on. The same thing happens also with things related to the quantum sort of. So the technology that emerges from the research in quantum physics is actually pretty advanced one, and I believe that it will be implemented in other things. For instance, you have superconducting circuits, so things like resonators and qubits and so on, but these things can be used for many other things. So you have nowadays, there's a lot of fertilization, there's a lot of interbreeding between different fields and between different technologies. You have superconducting detectors that are used today to detect photons so that you can have a clear-cut answer to the question of whether there is a narrow loophole in the Bell inequalities, for instance. You have the same kind of things you send in space to see better pictures of whatever your cosmic microwave background and so on. So you can see a better pixel somewhere out there, and you can make a theory, you can understand something a little bit better about the universe. The same thing happens in, I guess, in general in theoretical development. So the things that you would not address theoretically some 20 years before, you could address now just because there is some technology there that kind of stimulates you to ask these questions. So I see this in developing in many ways and fertilizing a lot of research fields. So you see now, to me at least, it's quite fascinating to see that quantum information can interact with fields as distant as cosmology. So we do have this on the table. It's quite amazing.
So I'll go back on the bet of or factoring when we will see quantum computer factor faster. That one is hard because you will need many quantum bits. Number much bigger than what we can control or you can imagine of controlling on the shorter amount of times. But I know of 3 groups who claims that they will have, in the next 5 years, 50 to 100 quantum bits. That they will be able. So with this, you should be able to do something that you cannot do efficiently classically. It might not be interesting, it might not be factoring, but at least it's a boundary, which I think would be an important milestone. And 3 groups are John Martinez, Mark Safman, and David Corey. Claims that, or they're working towards this, and then we will see. And I think it'll be important for the field, having that benchmark.
Okay, we have to finish up in the next few minutes. I know Chasla had something he wanted to add, and then I believe Carlo had a question. We'll see.
Yeah, I just want to say something about what we have overlooked so far, and it's not about quantum computation, but it's about quantum information. It's quantum key distribution. And I think in the view of an increasing threat of spying us all the time, it will be necessary to find ways to secretly communicate with each other. And there is a way of that. And I think just because there is a need for that, this will be implemented. And I will not that much worry about, the number of quantum algorithms. And honestly, I think it's just the case, as Andrew said. We don't know really what it is good for in 20 or 40 years. What people now doing when they perform their experiments on some Mickey Mouse 2, 3, 4 qubit experiments with some algorithms, they actually learn how to manipulate individual quantum systems. So they really want to learn how to perform individual gates, individual unitary operations. That was not possible in the past. And at the end, it might turn out as a kind of a quantum metrology, some precision measurement that will be decisive, maybe in testing some violation of the standard model or whatever kind of things that we can't really imagine right now.
Okay, did you still have a question? It's about 7:30. We should probably end it up. Okay, let's please thank all the speakers again.